The last period of the Paleozoic era was dominated by the giant supercontinent of Pangea, into which Laurasia and Gondwana finally merged. The Permian was named after the Russian region of Perm, because its limits were defined by strata found in the Ural Mountains. It ended with the largest mass extinction of the last 500 million years, when at least 90% of land and oceanic organisms disappeared. The sheer size of the Pangea supercontinent had significant implications for the world's climate and the spread of fauna and flora. The mountains blocked the humid, equatorial winds, with the result that deserts formed in the northern part of Pangea. Sandstone strata revealed the existence of huge expanses of dunes. As the climate became drier, large mammal-like reptiles appeared, better adapted to coping with the new conditions. In less arid regions, plants continued to diversify. The south part of the planet is a vast landmass that gave some faunas the opportunity to spread over a wide area. On the northern section of Pangea, in Siberia, one of Earth's largest eruptions of magma covered a huge area with flood basalts and was accompanied by outpourings of ash and gases, especially sulfur dioxide and water vapor. This coincided with the Permian mass extinction, when the oceans became starved of oxygen and most marine species died out. Most Permian sediments encountered are red beds of desert or river origin, with marine sediments less common. This is because of a drastic lowering of sea level, especially during later Permian times, and the emergence of the continental shelves. The consequences for invertebrate marine life were disastrous. The Carboniferous Permian glaciation, which covered so much of the land in the southern hemisphere, was largely over by mid-Permian times, and marine faunas proliferated. Yet by the late Permian the Earth witnessed the most acute biological crisis of all time. The mainly tropical crinoid, brachiopod and bryozoan-dominated ecosystems of the later Permian were destroyed completely, a process that took place over some 10 million years. All the continents were assembled into the giant supercontinent of Pangea, which must have affected climate and oceanic circulation, and it was no doubt an important factor in generating extinction. But most importantly, sinking, inactive mid-oceanic ridges caused the global sea level to fall by up to 280 meters, with great loss of habitat, and little sedimentation. Warm, shallow seas became reduced to certain parts of the world only. Massive volcanic eruptions contributed to environmental instability and thus to ecosystem collapse. It was several million years before normal marine sedimentation was restored. Rectifenstella was an upright, fenestrate bryozoan colony. It was conical with a net-like appearance, and was composed of thin branches, each of which divided into two. These branches were linked by small, usually horizontal partitions, which produced rectangular holes in the colony. Circular openings on one side of the colony were arranged in two rows. These were openings to the autozooidia, where the colony's individual soft-bodied animals lived. Each autozooid had a ring of tentacles around its mouth. Small, hair-like extensions on these tentacles would beat to create a flow of water that drove food particles toward the autozooid's mouth. The filtered water then flowed out of the rectangular holes to the reverse side of the colony. Acanthocladia was an upright, often bush-like, fenestrate bryozoan colony. The branches grew from a central axis and split in two. Sometimes, smaller branches fused together and irregular-shaped holes would develop between them. There were rows of circular openings on one side of the colony that housed soft-bodied autozooids. When the autozooids were not feeding, their tentacles could be withdrawn. The reverse of the colony was smooth, or had fine striations. Thamnopora was a branching tabulate coral. The corallites, which in life housed the soft-bodied polyps, were circular in cross-section and curved outward from the center of the branch. The polyp would have rested on the thin horizontal partitions. The walls of the corallites were perforated with pores and increased in thickness toward the edge of the colony. Horidonia was a strophomenid brachiopod. The slightly concave brachial valve, sharply curved at its anterior margin, sat inside the L. Arger, convex pedicle valve. The immature Horidonia was attached to the seabed with a stalk-like appendage. This withered as the animal matured, so the adult relied largely on the weight of its pedicle valve to stay put on the seabed. Coldium was a small rhynchonellid brachiopod with an opening beneath the beak of its larger valve. There was an outward fold on the forward edge of the smaller valve, which corresponded with an infold on the forward edge of the pedicle valve. The inside of the shell had a thin wall that rose above the floor of the pedicle valve. In life, this would have supported a small, spoon-shaped muscle attachment site in the middle of the valve. Xenodiscus was an ammonoid with a compressed, disc-shaped shell and flattened sides. The whorls on the shell overlapped slightly and it had a wide, shallow center. Its weak radial ribs were developed on the early whorls, but were more faint on the mature body chamber. The point where the internal partitions were joined to the shell is called the suture line, and it is the form of this line that separated Xenodiscus from the Goniatites. The suture line shown below is ceratidic and Xenodiscus is a ceratidid ammonoid, a group that evolved in the Middle Permian. It survived the end Permian extinctions. Gerizonites was a stout, round goniatite. Each whorl partly overlapped the one before it and it had a broad and fairly deep center. This type of shell is known as moderately involute. The shell surface was smooth and there were no visible patterns. Permiferous was an almost rectangular bivalve that had rounded anterior and posterior extremities. The beak on both of the valves were low and positioned toward the anterior end of the shell. The shell surface was smooth, but there were occasionally concentric ribs and faint radial patterns at the posterior end. The shell also had an angular shoulder that ran back at a slant toward the hinge. Internal features that cannot be seen on the specimen above included two well-developed teeth beneath the beaks on each valve and two more teeth parallel to them on the dorsal margin. In life, these would have helped hold the two valves together. Deltablastus was one of the last blastoid echinoderms to have existed before the group became extinct. In life, Deltablastus would have been attached to the ocean floor by a thin stalk. Compared with the similar-looking pentramites, which existed in the Carboniferous, there are some notable differences, such as the more developed upper circlet of plates of Deltablastus. Although it occurred much later than pentramites, Deltablastus is a survivor of a more primitive group of blastoids. Ditomapige had a distinctively prominent central region of the head or glabella that widened toward the front. Deep furrows in the rear of the glabella divided it into three lobes, a feature that distinguished it from the Carboniferous trilobite Hesselrides, which was otherwise quite similar. The thorax had 9 segments, with a raised axis and side parts that turned downward. The tail shield was about as long as the head and had 14 well-marked rings. Opening with a murmur and ending with a band, the Permian saw the rise of advanced synapsids. In the oceans, ray-finned fish continued to diversify, while terrestrial vertebrates evolved a new type or predator, the cynodont. Meanwhile, herbivores were perfecting sophisticated chewing mechanisms. The rise of advanced synapsids was the most important evolutionary event of the Permian, because it was critical to the emergence of mammals and, ultimately, modern humans. As the Permian progressed, the terrestrial fauna took on a more familiar setup, with relatively few predators feeding on the more numerous herbivores. The top predators of the late Carboniferous were sprawling in posture, demonstrating a less active mode of life, similar to many modern reptiles. By the late Permian, synapsid predators had evolved features that enabled active hunting. Their limbs had elongated and were placed more directly under the body, their teeth had differentiated into incisors, canines, and cheek teeth, and their eyes had moved farther forward, improving stereoscopic vision. The Permian ended with the greatest mass extinction of all, with an estimated 95% of all marine and 70% of terrestrial species dying out after volcanic eruptions poisoned the oceanic and atmosphere. Although a small, slender-bodied fish, acanthodes was well protected from predators, with paired spines on the front edges of its pectoral and pelvic fins as well as projecting from its dorsal and anal fins. More specific characteristics included a single dorsal fin set far down its back near the base of its shark-like tail, and closely packed, roughly rectangular scales. It had no teeth, However, it inhabited freshwater, where it lived as a fast-swimming filter feeder. Xenocanthus sharks have been described mostly on the basis of isolated teeth found in marine and freshwater rocks from all over the world. As in all other shark groups, two pairs of fins projected from the belly region, the pectoral fins closest to the head, and the pelvic fins closest to the tail. These acted as hydrofoils, lifting the shark as it moved through the water. The male had a pair of rod-like claspers projecting backward from the pelvic fins, used to deposit sperm directly into the female's body during mating. The final fin on its underside was the anal fin, which was divided into two parts. Its tail was completely in line with the rest of the body and the upper and lower lobes were about the same size. Archegosaurus was discovered in 1847 and was one of the first Permian amphibians to be described by scientists. Almost all Archegosaurus fossils come from deposits that formed on the bed of a deep lake. Modern narrow-snouted crocodiles such as gharial are fish-eaters, and Archegosaurus probably hunted in the same way. Some Archegosaur specimens have been found with acanthodes bones inside their bodies. Archaeops is one of the best known of the temnospondyl amphibians. A large number of specimens have been collected, and because the animal was large and robust, these specimens are remarkably well preserved. Archaeops was also unusual among early amphibians in that the entire skeleton was ossified, which is far more readily fossilized. Its contemporaries had more cartilage in their skeletons, and because these were not mineralized, their complete anatomy has not survived. Archaeops first appeared in the late Carboniferous of North America, but most specimens that have been found come from the early Permian. It was one of the top predators in its ecosystem. It resembled a short, fat alligator and almost certainly fed on fish and small amphibians. It probably underwent a change of diet during the Permian. Early specimens have a muzzle shaped like a rounded shovel with small, almost marginal teeth suitable for seizing small fish. However, later Archaeops had a longer, more rectangular snout with clumps of larger teeth at intervals, much like those found in modern crocodiles, which feed on larger animals caught at waterholes and in rivers. Sclerocephalus was a smaller relative of Archaeops. It lived in large, shallow, tropical alpine lakes that developed between rows of mountains across what is now Central Europe. In some cases the water became stagnant, and the large adults and small larvae of Sclerocephalus died together in large numbers. Seamoria was a small carnivore that, for many years, was considered to be close to the amphibian reptile transition. There was much debate as to whether it was a reptile or not until paleontologists noticed that its smaller relative, Discosaurus, had external gill and lateral line canals in its juvenile stage. This pointed to Seamoria being prereptile, and it is now considered to be a primitive amphibian tetrapod that parallel reptiles in some of its adaptations to terrestrial life. Unlike its larger cousin, Discosaurus seems to have been aquatic throughout its life, having external gills when it was young and lateral line canals throughout its life. Most specimens of Discosaurus have been found in the Czech Republic, in an area where the surface rocks represent a shallow early Permian lake that becomes stagnant, killing all the fish and amphibians in it. Thousands of specimens have been collected from this area, making it one of the most common fossil amphibians in existence. Diplocaulis is one of the most common fossils found in the Texas redbeds, but it has no living relatives. From the neck backward, it resembles a fat salamander, but its skull is a strange boomerang shape, with long, flattened horns on each side. One idea is that these horns acted like hydrofoils. By using them to manipulate the water current, it could gain lift or downward thrust, which enabled it to rise and sink with little effort. Orobaites, one of the first, most primitive vertebrate herbivores, is Knkown from a few complete skeletons found in an abandoned sandstone quarry near Bromacher in Germany. The fossils found in this quarry represent one of the first truly terrestrial reptile and amphibian communities found in the fossil record. It is the most primitive member of the family Diadectidae. These herbivorous reptiles were large for their time. They had broad back teeth for side-to-side chewing of vegetation, and longer front teeth for ipping foliage off branches. Captorinus was a primitive reptile with batteries of crushing teeth that were continuously replaced. It could have been an omnivore, feeding on smaller animals but also capable of grinding leaves or stripping twigs. Later Permian caprinids were almost certainly plant eaters. Mesosaurus was the first aquatic reptile that has been found. It represents a return of a small group of vertebrates to the water, about 20 million years after vertebrates adapted to life on land evolved in the late Carboniferous. It was a reptile, so it had waterproof, probably scaly, skin and long limbs. Because it had lungs instead of gills, it had to come to the surface to breathe. The tail was long and flat like a crocodile's, and the feet were large and could be used in swimming. Almost 200 long, needle-shaped teeth trapped small fish and crustaceans as Mesosaurus swept its long, narrow snout rapidly sideways through the water to capture prey. Scutosaurus was a large herbivore belonging to the Parasaur group. All parasaurs had long, thick ribs forming a barrel-shaped chest, the large torso contained an extensive digestive tract to break down tough plant material. Blunt teeth were capable of cropping vegetation, not chewing it. Its skull was broad and flat, and short, down-pointing tusks hung from its lower jaw and the sides of its face. Compared to other pelycosaurs, Varanops and its relatives were voracious predators, active and agile, with long limbs and sharp, backward curved teeth. The most widely distributed of the primitive synapsids, they have been found in the USA, Russia and across the southern hemisphere. In 2006, a skeleton of Varanops was reported to have bite marks, and scientists theorized that its remains had been chewed on by a scavenger before being buried and fossilized. The shape of the bite marks shows the scavenger to have been a large temnospondyl amphibian. This is the oldest evidence of scavenging among land vertebrates. Dimetrodon is often included in dinosaur books, and thus commonly mistaken for a dinosaur. It is an early synapsid, and in fact more closely related to mammals, with which it shares anatomical features, such as a single hole in the skull behind the eye. It lived in the early Permian, at least 40 million years before the first dinosaurs, and lacks dinosaur features, such as upright legs. Dimetrodon was among the largest carnivorous pelycosaurs and was the most fearsome predator of its time. Its high skull and relatively short snout gave it a powerful bite. The two canine-like fangs in the upper jaw were roughly located in the position of canine teeth of modern mammals, such as dogs and humans, and their roots extended through the bone all the way up the side of the face. Although they are not as striking as the saber teeth of big cats, they were powerful and deadly. In all, Dimetrodon had 80 large, pointed teeth, which show that it was specialized for killing other large land vertebrates. Moschops was a thick-skulled herbivore with stout legs and thick ribs that formed a large, barrel-shaped chest. It had a very large gut for digesting tough plant matter. Overall, Moschops was a heavily built animal, and full-grown adults probably had little to fear from the predators of the day. The Dinocephalians, which included Moschops, were one of the earliest therapsid groups to evolve and were very common in the first part of the late Permian. They diversified to exploit many of the ecological roles formerly carried out by pelycosaurs. Carnivorous and herbivorous Dinocephalian are known, but all of them have peculiar front teeth. Unlike those of other animals, the upper incisors do not overlap the lower incisors, but interlock with them, allowing effective nipping. Moschops may have formed small social groups or herds. Indeed, discoveries have been made of several individuals fossilized together. The thick skull is probably an adaptation for social behavior, such as ritualized combat. The mysterious Eothyrus is only known from a single broad, flat skull described in 1937. It is distinctive due to two large, fang-like teeth on each side of the upper jaw. The reason for this peculiar arrangement is not known. The remaining teeth were also sharply pointed, so Eothyrus was a carnivore. Although the prey must have been small because it was shorter than 30 centimeters, it is. possible that it hunted insects and other vertebrates smaller than itself. Surprisingly, it is related to the giant herbivore Cotylorhynchus. Cotylorhynchus was the largest of the Cassiids, a specialized group herbivorous pelycosaurs. It had the smallest skull relative to its body size of any synapsid. Although it had blunt, expanded teeth for crushing tough plants, most of the digestive work was done by the enormous gut, held within a barrel-shaped ribcage. Cassiids were highly successful and survived longer than most other pelycosaurs. They were still living in the late Permian when the rhapsids had become dominant. Edaphosaurus was a herbivorous pelycosaur with numerous blunt teeth that formed crushing plates. The teeth were not just around the jaws but also on the roof of the mouth and sides of the lower jawbone. Although it was herbivorous, Edaphosaurus was not related to Cotylorhynchus. One of the most distinctive features of Edaphosaurus is the sail crest on its back. Unlike the sail of Dimetrodon, small prongs branched off from the main rods that supported the sail, giving them the appearance of twigs. Despite this difference, the sails of Dimetrodon and Edaphosaurus probably evolved for the same purpose: trapping heat while basking. This meant that it could warm its body quickly in the morning sun and become active before many predators. The Dicynodonts were an extraordinarily diverse group of specialized herbivores that survived for longer than all other therapsid groups except the Cynodonts. Dicynodonts continued into the late Triassic, while Cynodonts evolved into today's mammals. The earliest Dicynodont known from good fossils is Robertia. It was relatively small, about the size of a house cat. Despite its early appearance, it shows recognizable Dicynodont features. For example, it has two large canine tusks. Although the other teeth are absent, it is likely that the canine tusks were used for digging. Prisonasuchus is one of the earliest cynodonts, a group of the rhapsids that gave rise to mammals. It shows the first signs of mammal-like cheek teeth, differentiated into premolars and molars. Other the rhapsids, and most reptiles, have only one kind of tooth in the side of the jaws, desp. Its advanced teeth, the body was still primitive. Dicynodonts such as Palaemonodon were stocky, pig-like animals with shorter tails than most other early synapsids. Their jaw mechanism was unusual, with a sliding jaw joint and jaw-closing muscles that were located behind the jaw and attached around the rim of the skull opening behind the eye. In addition to chewing food by moving the jaw up and down, like humans and many other animals, Dicynodonts could also move the jaw backward with each chewing stroke. This produced a powerful grinding motion that pulverized the tough plant material on which they fed. This adaptation must have been effective because Dicynodonts were one of the most successful groups of herbivores in Earth's history.